Okay, so make a start. So today in the final sort of methodological lecture, because we're going to move to these case studies next, we're going to talk about something that's very close to my interests. I don't walk around thinking about this all the time, but it's an area that the group works on in terms of research, and I think it's a really interesting area for moving the domain forward. So I think you've seen this plot before, and I brought it up when introducing emulation. So in this plot, we've got this idea that we've got the real world, where things sort of actually happen, and then we've got different fidelities of simulation that we can use to try and predict what's going on in the real world. And these different fidelities allow us to make predictions, but have different defects associated with them because they're sort of different granularities. So they might be doing things like operating at longer time frames or larger spatial scales, or they might be making particular approximations. So in a Formula One wind tunnel example, you might have maybe this simulator here is the wind tunnel itself, which is a form of simulator. You use a model car, it's a sort of physical simulator. And maybe these simulators are computational fluid dynamics with different ways of representing turbulence, which is a tricky thing to represent apparently in a CFD simulation. I've never done much CFD. And then this is the real world. This is how the car performs when you send it out in testing. And the notion is that we use emulators to try and adjudicate between these different sources. They represent our ignorance about the problem and then allow us to select from the different sources according to the question we're trying to answer. So key amongst this today is this notion of multi-fidelity emulation. In multi-fidelity emulation, you're going to sort of have an emulator that can do what these seem to be doing, which is they're joining between different fidelities of simulation in this emulator's case and the real world. So they not only do they end up with a sort of expressing their ignorance about the simulation, but they express their ignorance about the relationship between the simulations and the relationships between the simulation and the real world. And this hopefully allows us to start pushing our decision-making closer to the real world because we have the emulator as a framework that joins across the three. Now, let's be very careful again. It's clear that there's no way we could, well, it's very unlikely we're going to be able to build an emulator that can represent all the complexity of these underlying systems. So typically we're doing that in response to a particular question of interest, right? So the simulators are more general, the emulators become quite question specific for some question we're working on at a particular time. So what we're going to look at first is a very sort of simple way of looking at this. So this is known as a linear multi-fidelity model. And what we say is the high fidelity simulation is going to be composed of some fraction of the lower fidelity simulation, plus some additional function that is the error between the two. So we're basically saying that what we see as a high fidelity simulation looks like the low fidelity simulation plus some function over the inputs, and it may also be a fraction of the low fidelity simulation. So we can do this across multiple emulators if we, the highest fidelity being the T emulator and the next highest T-1, T-2, etc. We can compose our functions in this way additively to try and describe everything that's what's going on. And that's particularly nice if we're using Gaussian processes as emulators. So we end up with a data set, an input data set that now contains like the inputs that we choose for the low fidelity. A question, yeah?
Yeah, on the previous slide, is that error the modeling error of the low fidelity function? So the difference between the high fidelity.
Yeah, that's right. Yeah, yeah. So we can think, but it's the modeling error. Yeah, thanks for good clarification. It's the difference between what the low fidelity says and the higher fidelity says, and we're going to be uncertain about that as well. So now we're sort of emulating three things, but one is, so this is like, as you nicely put, and I should have said that myself, this FR is the sort of modeling error of the low fidelity relative to the high fidelity. It's not actually telling us the modeling error of that relative to reality. If we wanted to do that, we'd drop down here where T might be reality, T-1 might be high fidelity, T-2, if we summed it out. So I should have a sum at the front or something, shouldn't I? might be then the lower fidelity, and so on and so forth. So when you actually sort of implement this in code, what you'll tend to do is you'll have some set of inputs you want to test on the lower fidelity and some set of inputs you want to test on the higher fidelity. Now, I always do these things as design matrices because statisticians said that. So this for me is a set of inputs where each row contains a different input to the low fidelity and then a different input to the high fidelity. But we're compressing them into the same matrix here. This is the reason I'm saying this is because you'll see that this is how it's done in the code. Now, if we do that, what we can do is build a joint Gaussian process. So I'm sort of introducing to you multivariate Gaussian processes here, but there's a trick to the most general form of multivariate Gaussian process you can produce is a univariate Gaussian process. Okay, what on earth do I mean by that? So the way that we're producing this multivariate process is by stacking the functions. So conceptually, we can think of each of these functions as vectors, right? And we can think of them as samples from a multivariate Gaussian. So this is vector associated with low fidelity, followed stacked on top of vector associated with high fidelity. And what we can then write, because of how our definition before and properties of Gaussian processes, going back to the variance, if we know the variance, the covariance of this process and the covariance of this process, then we can immediately derive the covariance of this resulting process. So because two processes, if we add them together in Gaussian processes, the sum of two GPs has a covariance which is the sum of their covariances. So here, it's not quite like that because there's a scaling factor. So if we know the covariance of this process and the covariance of this process, the covariance of this process is going to be that covariance of that times rho squared. Why rho squared? Because the variance of this thing is rho squared original covariance because it's being multiplied by rho. So if you scale a Gaussian by a factor, rho, b, c, whatever it is, the variance of that resulting Gaussian is scaled by c squared. So what you see, if we just look at the marginal covariance, and the way you look at a marginal covariance in a Gaussian is if we want to know the marginal covariance of f high, then we put sort of mentally, I can't reach up there. The lecture theatre is too big. But if I was even taller, I would be able to put, I don't know, I maybe can do it on the video, but I'll try and put my hands over the sort of f low. So I'd block out f low, block out k rho and rho k low and rho k low here and the zero here, and just left. That's how we marginalize in a Gaussian. If we wanted to marginalize out f low, that's the whole point of the Gaussian process. We'd just be left with this as the covariance of f high. But what's nice is we can also compute the cross covariance. So the cross covariance here is the object that gives us information between the two fidelities of simulation. And the cross covariance in this case is just rho k low. K low sounds like J low, doesn't it? Cool covariance functions. K low, yeah. Right, okay. So was that, I mean, I'm sure that wasn't entirely clear, but there were notes to write it up. But let me just check if there's questions about what I'm saying there. This is a really beautiful trick. When you linearly combine Gaussian processes, you always get a Gaussian process, but it's joint over two functions now. So we'll come back to how we're going to represent that in the covariance. So it's a joint Gaussian process, but I'm trying to make it look univariate here. And what we're going to do to make it look univariate is we're going to push this, we're going to convert this low into an index, and we're going to push it into the covariance function. And then it will just look like a regular Gaussian process. Hopefully my slides do that next. So the overall x is now these x lows. So this is feature 0 of x low, feature 1 of x low, feature 2 of x low, so on and so forth. But what I'm adding here is an index. And here I've set the index to 0. And it's 0 if the function fidelity is low, and 1 if the function fidelity is high. So what I'm now doing in the covariance function, conceptually, this always works, right? If I want multiple outputs, I can think of what I do is I don't just tell the covariance function the input location. I also give the covariance function an index for the output I'm interested in. And because we're coding in Python, I'm starting indexing from 0. Yeah. So if I had a higher fidelity, I could add a 2 here. And now conceptually, what I can represent along here is the target values I see for the low fidelity and the target values I see for the high fidelity stacked on 1. So this ends up on top of each other. This is like a way of packing 2 functions into the same Gaussian process, right? You'll see other things being done. There's things called matrix variate normals and whatever else. They are always a special case of this. This is the most general thing you can do. The reason it's very general is because now you can specify these cross correlations between the functions in whatever manner you like, right? The classic thing to do, by the way, is just to assume no correlation. If you assumed f low and f high were independent, this would just be 0. And that's also, we can do that in this process as well, right? You just have to have Kronecker delta function checking whether the indexes were the same before you compute your covariance. So when you start using Kronecker deltas and things like that on the indices, that's how you build these covariance functions. So you'll see that happening in the notebook. You should be doing the notebooks because you won't consolidate what I'm saying here. Basically, I give you partial information here. And unless you go and do the notebooks afterwards, then you'll always just live on partial information, you know, which we all do anyway. So you're very good at it, don't worry. But, you know, you're not completing all the information in the course. Okay, so what we're going to do here is we're going to use the Forrester function. But we've got high fidelity observations of the Forrester function and some low fidelity observations of the Forrester function. So the sense is that we've got these 2 functions that we could try and approximate. One is high fidelity, that looks broadly like the Forrester function. This one is low fidelity. It's got some similar shape. It's giving us some information. And the concept is, why would you ever go to the low fidelity function? Why would I want to do this? Why would I ever, in this situation, go to the low fidelity function? Anyone? Yeah, cheaper to compute. Yeah. Yeah, you might not have enough high fidelity. So that's almost like when the cost of high fidelity is infinite. So I may have a restricted number from the high fidelity. How many planets do we have at the moment? 1, I think. Does anyone live on another planet? Right. So we've got, that's quite difficult, isn't it? Because when you do climate, you know, you've only got 1 observation of what Earths look like. It's quite expensive to create another one. They do it in Hitchhiker's Guide to the Galaxy. But you know, so sometimes you're constrained by things like that. You've only got 1 planet or 1 solar system that you can observe in. So that's a real constraint. But yeah, in general, we can think of those constraints as cost. Sometimes it's just the cost. The cost of running a wind tunnel experiment versus the cost of running a low fidelity CFD versus a higher fidelity CFD, which is a bit more compute. So the idea here is, you see, we've taken more point observations in the low fidelity function than the high fidelity, presumably because of some cost reason. And sorry, my legends sort of, across the, I have to leave these legends on, otherwise I forget year to year what I'm doing. But so they're very important, but they're a bit large and over and falling over the some of the error bars here. But you can see what's happening is we've got the low fidelity and high fidelity are actually sort of there. Here's the low fidelity, and this is the predicted low fidelity. So we've got enough data with the covariance function we've used on the predicted low fidelity to actually collapse our predictions and have a really confident sense of what that predicted low fidelity is. Now, we don't have enough data on the high fidelity because we don't have data in this region. So we're absolutely confident about the low fidelity, but it's informing us something about the high fidelity. It doesn't give us the exact form of the high fidelity because it's uncertain what the error is. The error itself is nonlinear. So it's a linear combination of 2 nonlinear functions, right? So it doesn't really know exactly what's going on in here, but it has some sense that the function goes up. Now, if we don't have that low fidelity, this is the approximation we'd get, right? It would just sort of, the mean function drops down. So you're seeing the white versus the blue here. Okay, does that make sense? So we're actually getting information from And of course, there's an assumption under here. If that assumption isn't true, this can be problematic. Is that clear? So how we're doing it, we're combining the two functions in that way because we've developed a model of the error. Of course, we've only learned the nature of the error in these sort of regions where we're seeing shared data. But the nature of that error is then being pushed across into this region. Of course, there could be problems if that error was like not stationary. So we talked about stationarity, didn't we? If the error was not stationary, if the error tended to be larger in this region here, which is absolutely possible, then this would not give us a good estimate. But that's the sort of modeling assumption that we're making. Okay, so what we're going to look at, though, we're going to extend that to nonlinear multifidelity. So in this case, we're going to have a situation where we're seeing two functions. One is sine of 8 pi x, and the other is this horrible nonlinear relationship, sine of 8 pi x, right? The high fidelity thing. So that's the sort of actual functional relationship, but this is the thing we care about. So conceptually, the thing we care about is that substituted into here, okay? So this is clearly not a linear combination of functions. And what happens, so this is what these two functions look like. So the low fidelity in yellow and the high fidelity in cyan. And look, we're not even seeing the high fidelity that much according, there's theories in signal processing, if you study them, about how often you have to observe a function with certain frequencies. We're not even seeing it sufficiently here. And if we look at the correlation between the two, so if we plot the low fidelity against the high fidelity, we can see this horrific sort of relationship between them, which is coming from that little function we saw before. And sure enough, if we try this with the multi-fidelity, it's all wrong, because we've seen so few observations from the high fidelity function, and we're being dominated by the low fidelity function, and we are only allowing linear corruptions. So what we end up with is an estimate of the high fidelity from the linear multifidelity GP, which gets it totally wrong, right? It's sort of missing the frequency and everything else because it's assuming that linear relationship. So what we'd really like to be able to do is go beyond linear. So if we're going beyond linear, this is the sort of notion that we have, that you can have some linear error. I guess maybe I should have called that, I can't remember what that's defined as, but possibly that should be F error, or maybe there's a reason that I haven't remembered year to year why that's not F error. We'll find out perhaps in a minute, or it'll be in the notes. But in general, with the multi-fidelity, the nonlinear multi-fidelity, we've got the low fidelity mapping through another nonlinear function, rho. So instead of rho just being a scalar now, the high fidelity is some nonlinear function, potentially nonlinear function of F low. Now, if we do make that assumption, we can recover this system. But how do we make such an assumption? Because there's nothing we've talked about. Well, how could we do that? What does that look like if people have seen stuff in other courses? How could we try and do that? That's going to be a nonlinear function. We could just put any. What if this were a neural network? Would that be a problem? People studied neural networks. I don't know. Hands up if you studied neural networks or played with neural networks. There we go, a few of you. So would that be a problem if this was a neural network? And if not, why not?
Just train a network to learn rho.
Yeah, so actually it's not a problem at all for a neural network. And why I'm going to make it into a problem. Why is it a problem for us, but not a problem for a neural network? So we could just, that's what all these TensorFlow will just differentiate through that for you now, and set a load of parameters and activation functions will move, and you won't even have to do any coding. It's like 2 lines, In fact, that's what deep learning is, putting like another layer on top of the output of a previous layer. If this is a vector valued function, right? So why is that trivial for TensorFlow or PyTorch or JAX or any of these things, but it can be problematic for us?
What is optimization?
It's true, but actually that's the same for neural networks, and people just find the solution anyway. At the back there.
Maybe neural networks that operate on that value or one single value and then function from very complicated as a distribution value instead of one single value.
I would say go to the top of the class, but you're already at the top of the class, right at the back there. So that's brilliant. Yes, absolutely. Yeah, because these functions are pushing uncertainty through. So that you can do all that with neural networks because you're just doing optimization, and that just means that you need the gradient of these functions with respect to their parameters, which we do as well, but the parameter functions are the covariance functions, right? But when we're pushing Gaussian, well, we're pushing uncertainty through nonlinearities, the gradient isn't sufficient. You need to be able to integrate over the system, and that's intractable. Integration is much harder than. So in general, it's a sort of weakness of the framework of neural networks is that you don't, I mean, that's what, there's this whole domain, I think, what's it currently called, Bayesian deep learning,
Something like
that is trying to do that for neural networks, but you've got to get a load of approximations out. And we have to do the same with Gaussian processes. So we'll come on to that in a minute. But if you do have a system like that, if you can do that here, you can learn, there is sufficient data there to learn this, this system, which is pretty cool. Surprising, isn't it? Because you don't really seem as if you've got enough data. So this is an example Andreas Damianu constructed. So there's it, that's the learned correlation between the two, if you've got this non-linearity in there. So that was an example constructed by Andreas. We were just, Andreas is a friend of both Carl Henrik and me, and I was saying I need to get a new picture of him where he doesn't look like he's just popping out of the circle there. But yeah, Andreas was a PhD student and postdoc, and they also worked with me in Amazon for a long time, and he's at Spotify now. And he did his PhD thesis on this idea of deep Gaussian processes, which are exactly that, but with stochastic processes. So trying to say, what if we take one Gaussian process and feed it into another, but then we do the job of looking at how the uncertainty propagates through. So that's what a deep Gaussian process is. And that kind of, that paper is like 2013, I think. And it's really targeting this problem of, I'm going to push uncertainty through a nonlinearity, and that makes nasty things sort of happen. So I can think of, like, you can think of in general, all neural network models are just composite multivariate functions. So this is what, it just doesn't sound, if you say it deep learning, then you get in Wired magazine and on the front page of the New York Times. But if you say it's a composite multivariate function, you don't. So, you know, and indeed the whole, like Jeff Hinton admits it, like the reason for using the term deep learning was to make it sound like everything else was shallow. So the notion is that this is a shallow model, because there was a time, believe it or not, in the community when these models were not dominating. And the reason they weren't, deep neural networks weren't dominating, was because of there wasn't enough data and compute to learn these structures. So people hadn't demonstrated at that point. There was no like, we're suppressing those things. Just with the data sets we have, they performed worse than the other models. So always bear that in mind, because people are now using them a lot on data sets where they're not the best idea. And we know that other methods perform better when data's low. So that composite multivariate function, and I emphasize multivariate because going in here is, it doesn't have to be univariate. It's not one output going into one input. We've already seen how you can have multivariate Gaussian processes. And it's the same thing with a neural network, right? What happens in a neural network is you end up with your multivariate functions, very simple. You have like these ReLU units, these rectified linear units, or whatever your choice is on there. And then you feed them into another set of ReLU units. And the point, you know, mathematicians would look at and say, well, what's the point in doing that? Because it's still a function. You know, it's just g of x, why write all that down? Well, the clever thing is that the properties of these individual functions you're composing together, you can create sort of structures which give the resulting function properties that you might be interested in, you might believe in, things like translational invariance for a convolutional neural network, or local sensitivity for attention, you know, and all these sort of things people are doing, all you know, these structures, if you start doing composition on these structures as well, you can do time-based models. So like recurrent neural networks and, you know, LSTMs, and you can sort of do anything, right? Once you're just going to join these functions together. And the reason you can do it is because today we have automatic differentiation software that's very powerful. We didn't have that like when I started in 1997, and I did start my PhD working on neural networks. We had to do all the derivatives ourselves. But when it comes to Gaussian processes, we're in the same situation. You know, automatic differentiation might help because it's useful to know the gradient, but it doesn't give us the whole answer of how to compose these functions together and fit them to data. So that sort of composite multivariate function, sorry, my Markov chain has gone off the side, right side of it. We can view this probabilistically as well. It's just a Markov chain. So the Markov chain here is going sort of that way, and here it's going that way. Apologies for that. But like, it's just so here, in some sense, this would be like the lowest fidelity, a higher fidelity, a higher fidelity, a higher fidelity, higher fidelity, maybe real world data, right? But we could also envisage a world where we don't observe in these intermediate things. So you've got deep Gaussian process, low fidelity, deep Gaussian process, higher fidelity. That's possible as well. Once you've got this structure, you can sort of do anything. So conceptually, what we're thinking of is something like this, that now that with the deep Gaussian process, you might have observations of low fidelity, then high fidelity, something like that, okay? So in the notebook, you'll find that there's, sorry, it just gets included again. I should have stopped this being included again. You'll find that there's an example just to allow you to compare a deep Gaussian process to a regular Gaussian process. I really like this Olympic marathon data. The reason I started looking at it was because there's this book, which I quite like as well, Rogers and Girolami, Introduction to Machine Learning. It's about 10 years old, but it's a really good probabilistic introduction. And they use data sets from the Olympics to look at, just play with stuff. And then I was giving, 2013, I was doing a Data Science Africa Gaussian process tutorial, and I was doing it in Uganda. And Stephen Kiprotich, who's a Ugandan runner, won the Olympic gold marathon that year and beating all the Kenyans, which got the Ugandans all excited. So I knew that it would win me a lot of friends to include Olympic marathon data as a example, which it did, because Uganda's, I think, maybe still true, only had, at one point, it only had 2 gold medal winners, Stephen Kiprotich and Akibua, who won the 400 meters hurdles in like the 70s or 80s. So, so it's also a cool data set because you can see it's descending over time, but there's this, right, number one, anyone here run a marathon? Carl has. Look at you, the rest one there. So what was your time?
Oh, I mean, I think it was 50 minutes. I don't remember having it back in Manchester.
Do you remember your time, the overall time? 50 marathon, 50 minutes. 15 minutes for a marathon. Well, yeah, marathons are like, so they're like 42 kilometers long.
Okay, that's not really good.
Okay, so
it was called a marathon.
yeah, so it wasn't a full marathon. Sometimes like half, it's like a sub marathon. Yeah, 15 minutes. Wow. Call Mike. So anyone done the full 42 kilometers? Good heavens, you lot. So only. No, so but what pace do you run like 5K?
5:20, 5:30.
Miles
per mile, yeah.
per mile. What do you know in kilometers?
It's like 1650, 17.
1650 on. Okay, so it's 5K, right? Yeah, so that's fast. That's it's really fast. So that's like really fast. So actually, that's really fast. So my fastest 5K is 20 minutes. It's 4 minutes slower than that, right? And that's running a 4-minute pace approximately. So Katie's running a sub 4 minutes. She's running down here somewhere. Yeah, this would be this is a 3-minute pace. That would be a 15-minute 5K. So when you're watching like marathon runners, none of you can keep up over a kilometer. Katie can, just about. For the first couple of kilometers, she could keep up with the international marathon, and the rest of you can't. Okay, unless you're running 15-minute 5Ks, which You may be, of course you may be. This is really fast. And this up here is a little bit faster than Carl Henrik and I would run a marathon. And what happened in 1904 is they got lost. The marathon was held in St. Louis and they had cars leading it for the first time. And the cars pushed up dust because they didn't have tarmac roads. And all the marathon runners got coated in dust and got lost. And only 6 people finished. And it was just a total disaster. So I think my fastest marathon is like 3 hours 40, which is probably up here. And Carl Henrik's probably down here. He's slightly faster than me over the marathon. Clear. Over the half, I think it's. So what I really like this data as well is this remarkable thing about, I love the fact that people have these lives, we don't even think about it. Here, amongst you, some of you are thinking, well, I have run a marathon in 2 hours, I just didn't want to say. You all have these amazing lives, and so did Alan Turing. So this is Alan Turing being reported on in 1946. This is the Amateur Athletic Championships for the year were concluded at Loughborough College Stadium, Leicestershire, on Saturday with the second and last day of the decathlon and the decision of the marathon championship. So here's Alan Turing, Dr. A.M. Turing, Walton Athletic Club, 2 hours, 46 minutes. Now, okay, today they're getting close to sub 2 hours, but this is the fastest, and that's 2 hours 30, and that would have been close to the gold medal time in 1946. So Alan Turing is only 16 minutes off the gold. He didn't actually get selected for the 48 Olympics, but he was a crazily good runner, particularly for the time. So he's around here, and he'll be up here somewhere in like 1948. So you could ask the question, if there had been a, what's the probability that Alan Turing would have won the gold medal in the Olympics? And you can do it by regression, because you can create a function of what that gold medal time is over this thing here. And you can use a Gaussian process. So that's what we're going to do. And there's the fit. And it's kind of a shocking fit. And why is it a shocking fit? What's wrong? What things are going wrong in this fit? Go ahead.
It captures the outlier later.
Yeah, it's skewed towards the outlier. Yeah, so that's one thing. This outlier is really forcing the variance up. So actually, there's only 20 odd data points, and there's only one outside the error bars. So these error bars are, in a sense, well calibrated, because 5% of the data is sitting out of these 2 standard deviation error bars. But in order for it to be well calibrated, it's inflated the variance up. And why is that? Because we have a homoscedastic variance, it's called, on the Gaussian process. We're just assuming constant noise, whereas what's actually happening, we'd either have to consider that as an outlier. I mean, it's a really interesting philosophical question. Is that an outlier, like a sort of like, should we use a heavy-tailed noise? Or should we view the world as, well, they didn't know how to organize marathons 120 years ago, so overall the process is noisier? Is it fundamentally that there's just broader noise there? So the Gaussian process in its vanilla form doesn't do a great job, but what we're going to do is looking whether a deep Gaussian process helps. And this is a deep Gaussian process fit with only 2 layers of deep Gaussian process. And what you can see is it's done something quite interesting. It's got what we would now call heteroscedastic noise. So the noise is larger on the left and it's less on the right. And it's even got some cool characteristics, like it seems that like the pace of marathon increase, it's like this is Second World War, right? Although you don't find much going on in First World War, but the pace of marathon increase, and it does look like we're sort of tailing off in terms of our ability to run marathons, which is perhaps not that surprising as we reach the sort of limits of potentially human performance. So that's quite nice. But the thing I want to sort of show you is that's an estimate of the variance, but because it's a one Gaussian process feeding another, this is non-Gaussian actually. So that error bar estimate is not actually necessarily a good way of viewing the uncertainty, because it's 2 standard deviations. So what I'm doing here is I'm going to drop some points through the thing. So I'm taking points at inputs and then sampling for each Gaussian process and then dropping it through again. So we'll visualize that in a moment, just to sort of show you what the distribution of data is. So you see that actually, certainly in this region here, these things are quite heavy-tailed at the bottom. There's sort of like, this is a very, like one of the samples even landed on that point. I mean, that's coincidental, obviously. But so this is probably non-Gaussian. This is probably quite fat-tailed up here. And then what we see here is that things are getting tighter. I would argue that that's probably versus what humans would expect. If humans were predicting, that variance is probably still too high. And that may be because we've only used one layer of nonlinearity. Maybe we would need to use two. But give you a sense of what that sort of nonlinearity is doing. Oh, it's broadly linear. So this is the first Gaussian process. So what it's doing is it's sort of layout. So it's going to a hidden value that, you know, is between these two Gaussian processes. And it's set up. So I said composite multivariate functions. Here for visualization, I'm looking at univariate functions. So it's one-dimensional input, which is time, one-dimensional output, which is this sort of layer one variable. And what we see is that the model has fitted, and I haven't gone through the maths, that's sort of Andreas's thesis, how we do this. The model has fitted this sort of function with quite a large uncertainty, actually, on this first Gaussian process layer. So the maps from these years to some latent variable. But what's quite interesting here is notice it flattens off. So it's broadly linear mapping, but at this point here, it flattens. And that's critical for the way the noise appears on the next layer. So very subtle shaping here. And the level of this noise is also critical, because at the next layer, what we see is this, a very confident function from that input layer. So remember, it was broadly linear. So in some sense, this is strongly correlated with the year input, this input here, right? Because we're getting strong correlations along this line here, apart from in this side here. And what you'll see is, look, all the data is stacking up in this region here. So it's sort of using the linear with uncertainty. That uncertainty is now being pushed through this nonlinear function, which does look like the shape of the final function we're seeing. But when that uncertainty is, so what we're seeing on here is large, is uncertainty of this size, right? Basically, as we're coming in these sort of early years. And when you push that uncertainty through that size there, that uncertainty gets expanded as it comes out again. So that's why you see, oh, so I have to go back. Thought I put it in again. That's why you see large uncertainty on the left, because it's uncertainty in going through a rapidly changing function that leads to large uncertainty out. Whereas on this side, the uncertainty is lower. All these points have been stacked up to be at the same point on that function, right? So across all that region here, 1980 to 2020, all the functions are being matched to the same latent variable. Not quite true, is it? There's a gradual change. So when this there's still uncertainty with where they're being mapped to, right? So there's still uncertainty. They're being mapped to here with some uncertainty. So it's just exploring this region here. And since that region is not changing rapidly, that uncertainty isn't changing. The input uncertainty has no effect on the output uncertainty. So in this region, the input uncertainty that it's learned is constant because it's a regular Gaussian process with constant uncertainty. But as it goes through the next layer, input uncertainty here, constant, going through rapidly changing function, increases the amount of uncertainty. Input uncertainty in this region, going through a flat function, decreases the amount of uncertainty. So you see this heteroscedastic effect. So all the deep GP's done in this case is sort of use this capability to give us some heteroscedasticity. It's quite interesting because the underlying mean function itself could easily come from a Gaussian process, couldn't it? I mean, it's not, this function is not a radical function, right? If I told you that was a sample from a one-layer Gaussian process, you would believe me. But the variance, yeah? So one of the really interesting things when you start composing these functions together, stochastic processes, not like in neural networks, is what it does to the uncertainty. And, you know, as you all work out in this course so far, we love uncertainty, we love ignorance. You still don't know what your projects are going to involve. It's because we like uncertainty. We'll find out soon. Okay. So actually, I like this. I have this analogy that I didn't include in the slides here of pinball. So you can think of like, in this one-dimensional case, you can think of like the whole system as being like a one-layer pinball machine. So you've got a ball coming in at the top layer. This is the years 1880 to 2020, but we only start at sort of 1896 or whatever it is. And then what I'm showing you with a straight line is I'm showing you where the ball mapped to in the middle layer, the latent layer, the unseen layer, and then where it mapped to again. Now, but each of these maps has a Gaussian process associated with it. So I've tried to visualize, because we can conceptually think of this as Brownian motion. So the balls are falling with sort of Brownian motion, a little bit like a leaf going into the first layer with that sort of uncertainty. I'm not then visualizing how that uncertainty changes. I'm just showing, again, the new uncertainty in the next layer because this is a separate Gaussian process. So what you can see is what's going on is, yeah, this is the linear bit. So if you visualize a linear function in this way, you would just see parallel lines going straight down. But what you see at the end here is the parallel lines start to converge to this region here. And then if you look at the second layer, well, it's doing this bit of nonlinearity. But then these points are just mapping directly through. So that's my way of explaining deep learning to sort of non-mathematical audiences. But what does that mean in terms of emulation? Well, there's a bunch of stuff we can now do because, for example, if we have a load of composite things going on in a climate model, we might have a composition of human activities, we might have an ocean model we care about, we might have a land model, we might have an atmospheric model. We can do things like compose our uncertainty from the emulators together. So this is the notion that we have in the group of deep emulation, that you can start stringing these things together. So not just do multi-fidelity, but also look at uncertainty within the emulation. So you care about the climate thing itself, but you go inside the climate simulator and you put in your emulators in the relevant parts to take care of the relevant portion of the simulation so you can run it faster. So I'm just going to finish on some examples of doing that you're going to see in the lab class. So very, very simple system that you've got there, which is a mountain car simulation. So it was like a reinforcement learning example back in 1997 when I started in the community, where you're trying to drive a car over a hill, but the car's not powerful enough. So you sort of send it up the hill the other way to gain momentum, and then it goes over the hill eventually. And it's a sort of relatively simple task, but of course it's fast to simulate. So what we've got here is sort of sketch up of what you implement in the notes, which is you've got the simulation of the car itself, right? Which, okay, is fast to run, faster than the Gaussian process, but we can emulate that. So we can emulate the simulation of that. And then you can emulate the things around it as well. So there's all these little parts where your emulators can appear and you can start to do things. And we also mock up a multi-fidelity example towards the end. So I just sort of show you, so that's the example. You've got this car, it's trying to get to here, but it's not powerful enough. So what you basically have to do, so I'll show you, so it has a controller, and the controller decides when to accelerate according to what its speed and distance is. So, but it also has dynamics. So there's some sort of input action force, which is the acceleration, that's what we control. And then it has some position and velocity. That's the other sort of aspects of where the car is. So that's telling us what the car dynamics are within the system. That's our simulator. And then we have this policy. This is a reinforcement learning thing about how we respond to that position and velocity. Again, in the notes, I'm going to sort of rush through it to make sure we get to the end, and I can show you all the pretty pictures. So in reinforcement learning, you earn a reward for hitting that task. So our idea is we would like to try and do Bayesian optimization on this system and find what the parameters of this policy are. Parameters of this policy here, these thetas, that give us the car that completes the goal. So we'd like to do that by Bayesian optimization, and indeed you can. But if you just start with a random linear controller, this is what you get. So this is like randomly, the car doesn't go anywhere. It tries to get up the hill, but it's not powerful enough, so it can't get up. If you do a sequence of Bayesian optimization, so 50 iterations on the simulator directly of Bayesian optimization. So the simulator itself has got inside it, to run the whole simulation, you're running for a certain amount of time, and then you've got a failed run. But inside that simulation, the car dynamics are being simulated thousands of times in order to work out what it should do. So if we play that one, then what we get is that the Bayesian optimization nicely learns the controller that says, oh, you have to go back and forth. By the way, when I saw this in 1997, like, people didn't even have data projectors. Everyone was giving talks on OHPs. So we thought reinforcement learning was really cool, because they could show talks where they did things like this. I guess modern reinforcement learning examples are a bit more involved. But then, so what we're going to do is that the standard Bayesian optimization was just a loop around the whole thing and ignore the underlying dynamics of the car. And what we can do for more data efficiency, so we're not running that dynamics enough as much, we can emulate the dynamics of the car. So we can do experimental design, fit a Gaussian process to the dynamics of the car. Now, in this case, the dynamics of the car are really simple and fast. But if they were really complex, if it was like a Formula One car or something like that, then this would be worth doing. So this next example is using a Gaussian process to model these sort of the changes in velocity and position, and training an emulator with 500 randomly selected points. So we're not even doing like uncertainty sampling or anything. And this is the view of like what the emulation looks like versus the simulation. And then we just run the example with, we train. So before, we've used 500 calls to the simulator to train the emulator. When we did that first example, we used 37,500 calls to the simulator to run it, right? So now we are going to replace that simulator with our emulator, which in theory is cheap, but we've only done 500 calls to the simulator by doing that emulation. And once again, you won't be surprised, because obviously this is a pre-recorded thing, that even with the emulator, we can get it to solve the problem. And the final example you'll see in the lab sheet is just the same thing again with multi-fidelity emulation. So we end up with like, we have a low fidelity version of the car dynamics and a high fidelity. And we end up with, I think, a larger number of low fidelity than high fidelity. And I just want to end the lecture by, you think, okay, so this has just been playing with mountain cars, but this, I think when I saw this video, because we were working on this is David Morrow, Paul Viola, and Ger Kimchi, none of whom work at Amazon anymore. I don't know what's happened to Prime Air, but when they did work at Amazon, we worked with them to build controllers for this object here that used exactly the techniques I've just been talking about, which is, this is the Amazon drone. And the amazing thing that it does, and I got to see this static before it was public, but it, the tricky part is what it's doing now, which is transiting from vertical to horizontal flight, right? And that turns out, so you have to do a lot of modeling to do that well. And yeah, I don't want to go into the details of that, but you know the Formula One examples I've talked about. Does that look a little bit like a Formula One car? Well, to me it does. To a machine learning person, it's just a Formula One car because it has all the same properties and characteristics as a Formula One car. It's even made of carbon fiber. Of course it flies, but so what, you know. That actually makes it easier to deal with the dynamics. You don't have ground effects. And okay, it's going to transit the other way. Now, the important thing about it, there's a video linked on here, is that in order to make this commercially viable, it has to have a certain range. So it wants to fly vertically for battery efficiency, because it's all batteries. And all the details of the technical details of that are all in the talk that's linked next in the notes. But it also has to be able to learn horizontally and take off and vertically, sorry. And I just think the other thing that is sort of remarkable about it is you sort of almost can't believe, this has nothing to do with the work we did. You almost can't believe that that can fly. It looks like a TIE fighter, doesn't it? The reason it can fly, because once you've taken off, you don't need large control surfaces anymore, right? So you want to minimize your control surface for maximum flight efficiency. So a beautifully designed thing that's all down to Ger and Paul and David and the team. But it was just really delightful to be involved in a small part of that, helping to use all the techniques I talked about today for the controller. And there you can see Jeff Wilkie presenting it. It's not shipped though. I mean, it's not shipped, I think, because of regulatory. Jeff Wilkie also doesn't work at Amazon anymore. Everyone involved in this project doesn't work at Amazon anymore. I don't know what's going on. Just realizing. But he talks about it a few years ago and what the vision in terms of the technical specs were and why it's important to get those technical specs right. I think probably the reason you don't see it shipped is it's all the regulatory stuff. I mean, there's a whole load of, I'm not sure, to be honest, I want to see drones flying all over the sky. And that's sort of not here in Cambridge, perhaps, but there are definitely places where you could imagine it happening. And I think that's all that stuff is quite tricky. So that's beyond the powers of emulation to solve. And so I'll stop there and maybe have time for a very quick question. We'll be able to do more questions on Friday, won't we? Because we'll have a sort of full You'll have a full session on Friday.
Yeah, exactly.
Time for a very quick question. I'll stop the video. Any questions? That's probably, if you say a very quick question,
Yeah.
it always reduces the number.
It's a good idea for Friday to